Welcome Mechanics of Materials students. This is our second lecture in the topic of beams, and in this lecture we're going to go over an example deploying our internal normal, shear, and flexural moment expressions for a beam with a combination of distributed loads and point applied loads. So we're just going to start out looking at our beam here. We have what is known as a simply supported beam. That means basically it is statically determinate from the standpoint of its support reactions. So over here at support A, we have a pin support. So the pin at A can't impart a moment, but it can impart a force, either vertically, which I think we're going to call the Y direction, or horizontally. It'll do both. And we're also going to call point A 0x, meaning point 0 in a distance along the length of the beam. We've got a roller support at B, which can only provide force in the upward direction. Vertical only, no horizontal forces can be supplied at B, and we can't supply any downward forces. So those constraints allow us, once we've taken this distributed load and resolved it into a single resultant force of 4,500 newtons acting at 2 meters from the end, and then we've resolved our 30-degree oriented single point applied load here at 4 meters from the end. We can apply conditions of equilibrium, and we can solve for our support reactions A and B. Okay, so to get our resultant force of 4,500 newtons, we first created an expression Q for our distributed load, just making a line equation, knowing that the distributed load was 0 newtons per meter at point A, and 3 meters over it was 3,000 newtons per meter. So Y equals mx plus B. No B because the distributed load is 0 at point A. So here's our distributed load function. It's in the negative direction because we've defined positive Y as vertically upward. So armed with that, we can solve for our support reactions. Vertically, support reaction, the support at A is giving us 2,611 newtons upward. B is giving us 1,440 newtons upward. Support reaction A is also giving us 771 newtons horizontal, pointing in the negative Y direction, because that's necessary to counter the X component of this 890 Newton point load. Okay, now that we know what's going on, kind of external forces, aka the support reactions, now we're going to start cutting the beam up, and we're going to write expressions for shear, normal, and bending moment internal forces acting on this right-hand cut edge everywhere we might cut along the beam. And so you can see there's some natural divisions we can make. Nothing is changing between 0 and 3 meters. So that's one good interval over which to integrate our functions. Then we drop out the distributed load, and so we might want to look at a second interval being between 3 meters and 4 meters. And we're going to stop just shy of this point load. Then we're going to look at the interval from 4 meters to the end of the beam, and at the beginning of that third and final interval, we'll pick up the point load and incorporate it in what's effectively the lower limit of integration as we keep integrating down the beam. So we're going to start with beam position 0 to 3 meters. So here we've drawn our little mini FBD. We've cut our beam on the right-hand side, but we can represent our support reactions at point A, upward of 2,611 newtons, and our support reaction is pulling this little section to the right with 771 newtons, and we have a distributed load Q of negative 1,000 newtons per square meter times X, for however much X we're considering. So the part of the beam we cut off, of course, is giving us a shear force downward of V and a bending moment in the counterclockwise direction of M, and then it's giving us a horizontal force normal to our cut edge of N. So we can kind of give N by observation. N is obviously going to have to be 771 newtons because it's going to be all there is that's going to counter this horizontal support reaction. Now, assuming that N was distributed uniformly over the beam, which there's not a lot of reason to think it wouldn't be, depending on how that support reaction grabs the end of the beam, and we knew the cross-sectional area of the beam, we could get our sigma xx from N right now. But, that's not necessarily part of what we're doing here yet, but it kind of gives you an idea of how useful it is to solve for those internal forces, because they do relate directly to stresses if those stresses are uniformly distributed over the cross-section, which they won't always be. But in the case of axial normal stress, sometimes it is. So on to the ones that are going to be a little bit bigger. So let's look at normal force, using our definition of normal force being, shear force. We've defined our distributed load as being the slope of our shear force with respect to position down the beam. So we can write in differential form a relationship between shear force and our distributed load Q. So we can say dV equals Q dx. Then we can integrate between 0 and some point x, somewhat shy of 3 meters. And inserting the limits of integration, we can say that the shear force at any x minus the shear force at 0 is going to be equal to the integral of that negative 1,000 newtons per meter squared x with respect to x. So we get a 1/2 x squared multiplied by 1,000. That gives us 500 newtons per square meter times x squared. We've already evaluated that between 0 and x, and of course at 0 it's 0, so we're just left with the upper limit of integration. We can evaluate the shear force that the left-hand side of that beam would have to give if x were all the way over at 0 at the support A. So imagine this section being shrunk down to where it was just here, and then V would have to be equal to the vertical support force given by point A, which is 2,611 newtons. So V at 0 is 2,611 newtons. So we can just put that right in there and then add it to both sides, and we get a parabolic expression for shear force and concave down. So further out you go, the lower it is. To get moment, we integrate again, and we include new limits of integration. So we're going to take this entire expression, V, and plop it into an integral. We're going to integrate m from whatever the moment is at 0 to whatever the moment is at some point x between 0 and 3, which is what we have here. We know that the moment provided by the left-hand side of that beam at A has got to be 0 because there's no moment being imparted by the support reaction, so there's nothing for that cutoff part of the beam to counter. So moment at 0 is 0. And so that just leaves us with this expression integrated with respect to x and evaluated between 0 and some x between 0 and 3, which is now a cubic function. This is obviously 0 when x equals 0, so we're just left with this expression for moment. So we have a parabolic expression for shear and a cubic expression for moment in this first 0 to x equals 3 meters region under that triangular distributed load. Okay, next section that we're going to look at is between 3 meters and 4 meters. So going back up here, we're going to be, we just finished this one. So now we're on to this middle one. So in this section, there's no distributed load. So our shear force is going to be constant. The slope of a constant is 0. So shear force is constant. Oh, it's constant what? What is it? We can get that by plugging in, because there were no point loads being added, here at the end. We know that whatever the shear force was at 3 meters under the distributed load, just as we left that distributed loaded area, is going to have to be the same as the shear force is all the way along, because there is nothing being done to change it. So we plug 3 meters in here, and basically that's being shown down here, and evaluate, and we get negative 1,889 newtons. So shear force, internal shear force on the right end of a cut beam is defined as positive in the vertically downward direction. We got a negative value. That means the beam that we cut off on the right hand side is providing an upwards force along that area, or along that portion of the beam, that length of the beam. Okay, so we have a constant shear along that section, through that section. Moment is going to be the first integral with respect to x position of this constant, so easy. Integral of a constant is just a linear function, so we integrate negative 1,889 newtons dx with respect to x, and we get negative 1,889. We're going to evaluate this not between 0 and x, but between 3 and x, because now we're only focusing on that section from 3 to 4, so our lower limit of integration is 3 meters. Likewise, we got to figure out, well, what was the moment at 3 meters? Good thing we've got an expression for moment from the previous section up here that we can pop in 3 meters just the way we did with shear, and evaluate what was the moment at 3 meters from the previous section, because those have to match unless there was a point couple being added. So the moment at 3 meters coming out of our distributed load section was 3,330 newton meters. So that's going to end up getting added to both sides, and we have to use our linear expression and evaluate its lower limit of integration at 3 meters. So that ends up giving us a total expression for moment. It's still a downward sloping line, but it's got a pretty hefty constant offset. Throughout this whole section, our normal force hasn't changed because there's been no normal forces added. So the right hand side of the beam we've cut off is still exerting that 771 newtons to counter the horizontal force back at the support. Okay. So moving on to our last section. So we still have no distributed load. So we know that the shear force is constant. The internal shear force is constant, but we now have passed this point applied load upward of 445 newtons. Now we noticed back in this section the shear force was negative in the downward direction, which means it was in the vertically upward direction. So the shear force imparted by the right hand side of the beam that we'd cut off is pulling the rest of the beam up. Now we've had a point load that is itself pulling things up. So the shear force doesn't have to work as hard. It can think about it. So rather than the shear force being negative 1,889, it only has to be negative 1,444. So we basically added 445 to that negative 1,889. And it stays constant at the negative 1,444 all the way to the support at B, which just so happens to be 1,440. So those two can be thought of as effectively canceling. So when you get all the way to the support at B, the B support provides that shear. So that's actually going in the correct direction sign-wise. So let's go look at moment. So we can write the differential expression for moment here with a negative 1,440 newtons. Integrate that between 4 meters and some x. We can look at, well, what was moment at 4 meters? We can go back to our previous expression for moment here, put in 4 meters right there, which you can see being done. Trust me that it was done. You can plug in 4 meters for here and evaluate that expression. Meanwhile, we need to include our lower limit of integration over here on the right hand side of our expression. So we end up with the moment anywhere at any x between 4 meters and the end of the beam minus the moment at 4 meters, which we get up here, equals negative 1,444 newtons times x minus negative 1,444 newtons times 4 meters, the lower limit. So we can create a line expression for that. Notice we didn't have to add in any point couples like we did the point load for this section because again, we don't add in a step if we just have an applied point force if we're talking about our moment equation, not like we did up here where we added that step to shear. If we had had a couple acting at this point like so, then we would have added something into this lower limit, but we didn't. What we did do though is as we came across this point applied force at 4 meters, we can notice that it was providing the 771 newtons. In fact, that the support at A had to counter in our whole body free body diagram. So at this point, the cutoff right hand side of the beam doesn't have to supply that anymore. So if you look at internal to the beam as we cross that point at 4 meters, that point applied force that's heading up at 30 degrees has now completely provided all of the countering force to the horizontal force to the support at A, and that normal stress in the beam should drop to 0. So basically that would be something important to note, that if we're looking at axial stresses in the beam, N dropped to 0, so our sigma XX dropped to 0 as we went through the point at x equals 4 meters. So from 4 meters onward, N equals 0. And that pretty much wraps us up. If we've checked against our N support and noticed that our shear is countered by our N support, and if we put in 5 meters for our moment expression, we can solve this expression. Notice moment goes to 0 at x equals 5 meters, which is good because this roller support is not capable of supplying any moment. So evaluating your internal shear and bending moments and axial normal forces at your end support and making sure that it is only what that end support is giving you is an excellent way of checking your math to make sure you haven't made a sign error or forgot a lower limit of integration. So important things to do, steps to deal with these beams. Always, first, solve the whole beam FBD. Solve for the support reaction. So you may have to get some equivalent force resultants for distributed loads, figure out where to put them, then know what's going on at your supports, then start at the right or the left side, define your X however you want, and then then put that cut section in static equilibrium using the fact that you're going to have internal forces in the axial shear and then a bending moment capable of being produced by the rest of the beam. So you'll always have 3 unknowns that you'll be solving for. Force in the X, force in the Y, and moment for a 2D beam. Have more for a 3D. And at that point, you're going to be leveraging your differential integral expressions, Q, V, and M. Basically, integrate to get upwards from Q to M, take derivatives to get from M to Q, and the trick is always, always, always the limits of integration. Do not forget that you're integrating, you're basically going through definite integrals on both sides from one end of an interval to the other end. So you're not just going to integrate with respect to X, you're going to integrate with respect to V and X, or M and X. So what was the moment at the lower end where X was at your lower limit? So if you keep track of all those, keep track of signs, you'll do fine. And of course, your final check is, do N, M, and V at an X corresponding to the end of your beam correspond to what your support at that end can give? That's your final check. So if it isn't, then you have to go back and look for a boo-boo. So that is the end of this lecture. And just to give a quick look ahead, I won't walk through it, but the next page here is just gives a graphical depiction of what we just derived. So I will let you take a look at those in the notes. But this shows basically our cubic expression for moment in that first portion, parabola for shear, linear for distributed load, and further on out. And of course our 0 point for shear corresponding to an extrema which turned out to be a maximum for moment. And this point right here, looking ahead to our bending axial stress section, which we're going to do next, is going to be a point of great interest to us on that beam and beams like it. So we'll be looking ahead. The next lecture, lecture 3, we will pick up with longitudinal stresses, where we will go back to this point, or points like it on a beam, the points of maximum moment, internal moment, and say, what's going on with the stress all across the cross section of that beam in response to that moment? And we'll take a look at what's going on and derive an expression for axial stress due to bending moment. And it turns out that's one of the big limiting design factors in beams. So stay tuned.